Right. So we were having discussion on this Biot-Savart law, and now you have understood. Okay. Let us go for finding out direction of magnetic field. Right. So as we have already discussed in this Biot-Savart law that dB is equal to mu 0 by 4 pi I dl r or I dl sin theta by r square. Okay, and this theta is the angle between this ideal component and r. This theta is the component. Now, when theta is equal to 0, it means what? Magnetic field is parallel. Yes or no?
Yes, sir.
To the current carrying element.
Ideal.
Therefore, the magnitude of magnetic field will be equal to 0. Will be equal to 0. Okay. Another case. When theta is equal to 90 degree, it means magnetic field is perpendicular to position vector. We are not finding magnetic field with respect to ideal. Why? Because we are finding magnetic field at some particular point. At some particular point which is at a distance of r. So in that position vector itself we are finding out magnetic field. Okay. So magnetic field we are finding on the basis of the position vector. Okay. So actually the angle what we are making, that angle we will be making it between, you can say, this theta. What this it will be making, right? So on the basis of this position vector r at point distance r. Okay. Now whether it is perpendicular or whether it is at some angle with respect to the position vector r. Okay. When theta is 90 degree, this magnetic field is perpendicular to position vector, and the magnitude of magnetic field will be maximum.
Yes, sir.
Will be maximum. Now one thing we need to remember regarding its direction.
Yes.
Okay. Now we will be discussing about direction of magnetic field. Direction of magnetic field. Very important part. Direction of magnetic field, because everywhere you need to say about direction. Whenever you are calculating magnetic field, you have to speak about its direction first. Okay. So now, direction of magnetic field, how we will be finding out? So we will be finding this magnetic field direction with respect to Fleming's right hand rule. Okay. So Fleming's right hand rule. We will be utilizing Fleming's
Right hand rule.
right hand rule. Okay. So Fleming's right hand rule.
Yes, sir.
So if you are expressing with your thumb the direction of current, if you are expressing, okay, the direction of, so what will be the direction of current carrying element? Ideal will always be in the direction of current.
Correct.
Ideal will always be in the direction of current. So if this direction is there in the direction of current, if you are keeping your thumb in the direction of current and your finger should express in the direction of position vector. In the direction of position vector. Okay. Then if you curl your finger, then this curling of the finger will show you the direction of magnetic field. Okay. So in this direction, if you will be saying if the current is moving upward and R is in this direction, and if you are making the curl of the finger, so it is showing that this magnetic field is towards the board, into the plane,
Yes.
into the plane of the board. Okay. If suppose current direction is reversed, if current direction is reversed,
Then that's it.
okay, then it will be away from the board, out of the board, out of the plane of the board. Okay, understood now? Go ahead. And for into the plane, into the plane of the board, better I will be writing there where we are discussing direction. Okay, Fleming's right hand rule gives the direction of magnetic field. So the thumb of right hand points in the direction of
No.
current carrying
Correct.
current carrying element, which is the same direction of current, which is the same direction
Of current.
as the current has, and fingers extended in the direction of position vector R.
Yes, sir.
Position vector R. Then the curl of the finger will give the direction of magnetic field. Yes or no, gentlemen?
Yes, sir.
Yes. Okay. So fingers will give the direction of magnetic field. Generally, what notation is used, that if it is written as cross, it means it is pointing into the plane of the board. Okay. So this direction means into the plane of the board. And if simply only dot is given, then it is out of the plane of the board. Why we are talking every time about into the plane of the board and out of the plane of the board? Why? Because in x and y axis we are taking either current carrying element or position vector. Okay, so that z vector is always either it is moving towards board, going into the plane of the board, or away from the plane of the board. So along z axis only it is being calculated. Okay, so that z axis is showing into the plane of the board or out of the plane of the board. Okay, so if current direction changes, the direction of magnetic field also changes. Okay, so that point also will write. If direction of current changes, direction of magnetic field also changes. Yes or no, gentlemen?
Yes, sir.
Right. Okay, will I note it down? Okay, please note it down. Okay. Now we will be having some discussion between electric field and magnetic field. Difference between electric field and magnetic field. Just a small discussion we will be having. So, can I rub this side?
Yes.
Okay. So, difference between electric field and magnetic field.
Yes.
Okay. Whether we have noted down this one? Right. We will have a discussion on Fleming's left hand rule also later on.
Yes.
Okay. So Fleming's right hand rule is generally used to find direction of magnetic field of a current carrying element. Okay. Always fingers, if the thumb is pointing in the direction of current, the curl of the finger will be giving you the direction of magnetic field. Okay. Right. Okay, finished?
Yes.
Right, so we had a discussion on that magnetic field. So magnetic field, if I am writing here, so sorry, magnetic field already it is mentioned here. If electric field I am writing, then it will be 1 by 4 pi epsilon 0 and q by r square. Right? So this was electric field and this is magnetic field. Now what is the difference between these two? You can say that in terms of their range. In terms of their range. What is range? Means how much distance that effective electric field is effective or magnetic field is effective.
Both are same.
Okay. Effective means what?
Like their
Influence on that particular charge. Force applied on that particular charge. So it means if some force will be applied on that particular charge in the vicinity in that electric field, that is called range. Okay, range is the distance up till when that force will be applied on any particular charge. Right? So now you can say that both are long range. In terms of range, we can say both are long range. So both are long range and depends on inverse square. Depends on square only. Okay. So depends inversely on the square of the distance.
yes.
Where electric field and where the fields are calculated. Where the fields are calculated. Second. Okay?
Yes.
Now second is what?
Angle difference.
Yes?
Angle difference.
Angle dependence. Okay, very good. So we can say that magnetic field is angle dependent. Huh?
Yes.
Magnetic field is angle dependent and electric field is angle independent.
Yes.
Okay. Now what it is there? One major difference. This electric field is created by this Q.
Charge.
This Q.
Yes.
Electric field itself is a vector. It is having its magnitude and direction both. But this Q is not having any direction. Magnitude is there. So Q is a scalar quantity. So you can say that this electric field is created by a scalar quantity charge, scalar source. Whereas magnetic field is created by a vector source. Ideal is a vector. Okay, ideal is a vector. So third point, what we can write? Electric field.
Sir, DL is a vector.
Which one?
DL is a vector.
DL is a vector. Ideal is a vector.
Okay.
Ideal is a vector here.
So combined domain is vector.
Ideal is a vector. I is not a vector. Ideal is a vector. Okay? Because ideal we are taking direction.
Yes, sir.
Direction we are taking.
Yeah.
Okay, without taking direction, its calculation is not done.
Yes.
So ideal is the vector. Okay. So electric field is created by a scalar quantity called charge. Right? Here also charge is there. There also charge is there.
But scalar is vector.
No. But their charge is static.
Static.
Their charge is moving. So that charge is moving. I means what? The charge is moving, electron is moving, flow of current or flow of charge only is current. So if current will be there, moving charge will be there, then only magnetic field is created, otherwise it is not created. Lorentz force clearly stated that when there will be a V to the charge, velocity will be there to the charge. Okay, it will be moving at constant velocity, then only magnetic field will be created. Okay, so there also charge is there, here also charge is there. One place charge is static, one place charge is moving. Okay, so electric field is created by a scalar quantity. We will be writing only scalar quantity. Leave it as charge, because here also charge is there also charge is there. Charge only is creating. The only difference is one is moving, one is static. Electric field is created by a scalar quantity, whereas magnetic field is created by a vector quantity, and that is ideal. That is ideal. Due to that ideal. Okay, here we are writing ideal. There we are writing only Q. Only Q charge. Okay, so quantity ideal. Right, very good. Fourth one. So electric field is in the direction of the displacement vector of the charge. Electric field is in the direction of displacement vector. Okay. Whereas magnetic field is in the direction of is in the direction of it will be in any direction depending on ideal and R. It depends on ideal and R. Okay, it can be in any direction. It is not specified in one particular direction only. Whereas electric field always it is specified in one particular direction. Correct or not?
Sir, but it will be mutually perpendicular. All three.
It will be
mutually
so
perpendicular.
you can say that magnetic field will be perpendicular. Magnetic field will be perpendicular to the plane containing ideal and R. Okay, so what we can write here, electric field is in the direction of displacement vector, whereas magnetic field is in the will be perpendicular.
Yes, sir.
Magnetic field will be perpendicular to the plane containing ideal and R vector. Yes or no?
Yes, sir.
So these are the major difference between electric field and magnetic field, and in examination questions will be
Yes, sir.
Okay, this question also it is very important that what is the difference between electric field and magnetic field. Okay? Right. So just note it down. Then we will discuss on application of Biot-Savart law.
Yes, sir.
Okay.